All right, so hello class. This is the second lecture in our course on LMI methods in robust and optimal control. And this lecture is going to serve as a mini course, so to speak, on optimization. So if we're going to study optimal control, it makes sense that we should learn the basics of optimization. And there's two parts to this, of course, right? We want to do optimal control, so we're optimizing something, obviously. But then the other part, so there's optimal. And then there's this other part, right, which is also optimization, which is the LMI part. So we're going to use optimization algorithms to solve our optimal control problems. So we're going to be reformulating an optimization problem in controls as another optimization problem which we can solve. So the tools that we use to solve control problems have shifted a little bit, especially with the use of optimal and robust control, from what used to be sort of matrix calculations back in the day of least squares to graphical methods in the 50s, to algebraic equations that we could solve, Riccati equations and so forth. And then nowadays, the tool of choice is sort of real optimization algorithms, so for linear programming, semi-definite programming, and so forth. Right. So obviously, there's lots of reasons we need to cover optimization, and so that's what we're going to do today. So optimization. Right. This mini course, right, is going to introduce a couple topics, right, a couple important topics. First of all, what is optimization? And obviously that's important. But that's not all. We're also going to cover, so that's the basics of what an optimization problem looks like. But we also need to cover things like how to formulate your problem, right? Sort of basic, what is your problem? You have to think about it quantitatively, and how to formulate that as an optimization problem. Problem to an optimization problem. And then we're going to actually do it a little bit backwards. So we're going to talk about how to reformulate optimization problems, right? So how to take one optimization problem, and there's lots of optimization problems which are equivalent to that problem in some sense. And so we're going to talk about equivalences between optimization problems, how to move from one to the other. And that's a little bit out of order because the goal, so part of the problem is formulating our problem as an optimization problem, which isn't too hard. But then ultimately the goal is to formulate that optimization problem as one you can actually solve. So particularly convex optimization problems. And we're actually only going to cover that at the end of the lecture, the convex class of optimization problems. So really, we're going to be talking about tricks for changing your optimization problem from one form to another. And then at the end, we'll say, well, what form are you aiming at? Well, you're aiming at the convex optimization problems. And then the idea is that you can take those tricks and then use it to reformulate your problem as a convex optimization problem. So there's several steps to this. So we'll cover them one after the other. Right. So the first slide, right, is an introduction to the problem. And actually, I covered this in Lecture 1 to some extent. So in Lecture 1, we tried to cover the entire class. And now we're gonna come back to that formulation and restate it. So I restate it in a way that maybe dates me a little bit. So I don't know how many people have seen the movie City Slickers, right? So it was City Slickers. I think it was popular in the 80s, right? So I sort of grew up in the 80s. I've seen it, right? Billy Crystal in it, very famous movie. or was at the time. In any case, so there's a nice story from this movie where, okay, so the premise of the movie is that Billy Crystal's like a city slicker, and he goes out on one of these like cattle drives, right, with a real cowboy, Curly. That's Curly there. He's a cowboy. In any case, Curly, right, is not impressed with the city slickers because they're also complicated and they don't really understand life and so on and so forth. And there's one nice scene by the campfire when Curly, Billy Crystal's talking about all his problems, and he doesn't know what to do. And Curly, gives him some advice and says, you need to forget all this, right? You know what the secret to life is. Do you know what the secret to life is? That's what he asks, right? Billy Crystal. And Billy Crystal says, no, okay, illuminate me, O cowboy. What is the secret to life? Right. So Curly says the secret to life is one thing. Just one thing. And if you stick to that one thing, the rest doesn't mean, anything, right? Doesn't mean, he put it more colorfully. But that's Curly's statement. But there's a lot of wisdom in that, right? Because in truth, any problem, any thing you're trying to do, in fact, all of life, I suppose, the meaning of life, what you're trying to do in life, right? Anything, if you think about it rigorously, comes down to one thing. One thing. Now, it can be a combination of lots of things, but it has to be a linear combination, and essentially what he means is the objective function, what you're trying to maximize with your variables, the things you can control, and the constraints that life imposes, and so on and so forth. Right. So this is the one thing, the objective function. Now, the objective function can have a lot of pieces to it, right? It can be a combination of lots of weighted terms, right? So maybe how much money you make is one of those terms. It can be weighted by your added to a weighted happiness. Maybe there's some bilinear terms in there. Doing good, or the future of humanity, your children, right? There could all be in there, but they also all have to have weights. And in the end, right, you can't optimize more than one thing at a time, right? So you have to have an objective, and if you switch back and forth between things you're optimizing, you're never going to get to a solution to any of the optimization problems that you should be solving, right? So it's important to know that your problem, you may have not figured out what the objective function is, but there is one, and unless you decide on that one thing, you're never going to be able to converge to the solution to that one thing. You'll never be able to choose your variables which give you the best result. Right? So I thought that was very good advice, and so I put it in the first slide. Right, very important. Right. Okay, so but mathematically, what does that mean? Right. So it means that the problem, whatever it is, can be formulated with three parts, which we mentioned earlier. Right. The first is, and I'll skip the objective for now, is the variables. These are the things you can control. Things you can choose. Things you have flexibility around. Right? So which way you go to work, what job you choose, which classes you take, and so on and so forth. Right? Those are your choices. Right? And so this very concise X in F formulation of that means that your choices of variables have to lie in some set. So this is your sort of possible choices, and the variable is constrained to lie within that sort of range of possible choices. Now, it doesn't need to be numbers, right? It can be ultimately we would like to come back to numbers. But we can think of these variables as vectors, as matrices, functions, Systems themselves, right? Dynamics, locations, directions. They can be binary or discrete choices like colors. What color you want to paint your room, for example. Ultimately, though, all of these choices, no matter what they are, even if they're colors, right, can be represented using numbers, right? So you can choose red equals 1, blue equals 2. Green equals 3, and so forth, right? So we can make these numbers. We could add more flexibility, right? You could choose, don't have to be discrete, right? We could choose our RGB spectrum, so our weighting on red, or weighting on blue, or weighting on green, and so forth, to get a sort of continuous set of variables. But in the end, we want some numbers associated with these. And right, in our prima facie formulation of the problem, right, it doesn't really matter how we assign the values to numbers, but we have to at some point assign these values to numbers. Okay. So that's the variables. First thing you want to consider: what can I change? The next is what I'm trying to do. Right? What's the meaning of life? And that's the objective function. Obviously, it should depend on the variables. Right? If your objective doesn't depend on a particular variable, a particular choice, well, we can let's still leave it in for the moment because it may influence our constraints. So, but the objective itself does not necessarily need to depend on all the variables, but it should depend on variables. You have to be able to influence it at some point. If it has a constant term, right, which you can't alter, right, then you can just leave that off of the objective function. Okay. So it specifically has to assign a scalar value, and it's important that it be scalar because we can't optimize more than one thing at a time. Right? Scalar, very important. There is multi-objective optimization, but it's really sort of it's a dodgy field, and in the end, they usually mostly reduce it to scalar optimization anyway. Right? So there's a Pareto optimal front, but I'm not going to get into that. Right? So anyway, you have to assign for any choice of your variables, you have to assign a objective value, right? What's the value? And it can be minimization or maximization. In life, we try and maximize things, although I guess we could minimize pain, right? So there's no real difference between minimization and maximization. You can just put a negative sign in front of the objective, oops, and then it becomes the same problem. That's our first trick, by the way, for reformulating optimization problems, right? Min, max are equivalent, right? You just put a negative sign in front of the objective, and it becomes a maximization problem. Right? So no difference there. So right, there's our objective function, and then of course one of the most important parts is constraints. Once you've defined what it is you're trying to maximize, and there are variables you can choose, then we have constraints on our choices, right? So, right, if they're out of blue paint, right, then that imposes a constraint on our choice of variables. Or if we have to travel to Goodyear, for example, to get blue paint, well, then that adds another variable, which is how far we're willing to travel, and that goes into our objective function. But in the end, right, there's some constraints, right, which link our optimization variables together. There are unconstrained optimization problems, and certainly they're very important. But typically, in our first formulation of the problem, we usually have some kind of constraints. And those serve the purpose of linking our variables together, okay? Coupling our variables. So there may be things we can control which don't appear in the objective, but they do appear in the constraints, and so they're part of the optimization problem. Okay. So these constraints define what we call the feasible set, which is a set of valid choices. I'm not sure I would say valid, but the set of acceptable choices, minimally acceptable choices, right? So in the feasible set, if you don't look at the objective, there's no difference between one set of feasible choices and the other. What distinguishes one feasible choice from another is the objective function. But in the constraints themselves, they're all equivalent. Right? Everything in the feasible set is equally valid, right? As long as they meet the constraints. And here we've formulated it in this form, right, with inequalities and equality constraints. Right? So equality constraints are, say, if I have apples and oranges, right, and I want my total number of apples and oranges to be less than or to equal to 12, for example, then, right, that's an equality constraint. Number of apples plus number of oranges equals 12. If, however, I want my number of apples and oranges to be less than 12, right, that's an inequality constraint. And so that would go here. Apples plus oranges, A plus O is less than 12. And here we got apples plus oranges equals 12. Right? So different types of constraints. And this is a little bit tricky, putting your constraints into the form of inequalities. But if using the tricks we learned in this lecture, it can always be done. Okay. So that's optimization problems. So now we sort of go over the outline of this lecture, right? So the first thing we're going to cover again, right? This is like a little bit backwards, right? Because ultimately we want to formulate our optimization problem as one which is solvable, right? So we start with sort of our prima facie optimization problem, or the one we just come up with right away. And then we would like to use these reformulations right here to come up with one which is solvable. And which ones are solvable? Well, we cover that at the end, so it's a little bit dodgy to do it that way, but that's what we have. So basically, I'll just tell you, right? The solvable ones are convex optimization problems. We haven't defined what is a convex optimization problem. That'll come at the end of the lecture. But know that there is a class of solvable optimization problems called convex optimization problems, and your constraints and your objective have to meet certain criterion in order to be considered convex optimization. Right? So convex objective, basically, and convex constraints. So in this class we're almost entirely going to be dealing with convex optimizations with a few exceptions. For example, in the first homework we have some non-convex optimization problems. And so I hesitate to say only convex optimization problems are solvable, because there are some other ones which are solvable for reasonably sized problems. The most well-known is the mixed integer linear program problems, but we'll come back to that later. Okay. So initially we're going to talk about reformulation of optimization problems, showing how to convert your optimization problem to an equivalent one. We'll talk about what it means for two optimizations to be equivalent. Right? Equivalent being the operative word there. Right? So two equivalent problems may look very different, but basically, two problems are equivalent if a solution to one can be used to solve the other. Right? And there's a wide class of problems which are equivalent. Right? So that's the outline of the lecture. Okay. So we'll start by giving some examples of optimization problems, perhaps the most well-known ones, and maybe tell a little story here and there. So first, we'll cover one which you probably learned in high school, which is the least squares optimization problem. Okay. So hopefully you've learned this, but I'll just restate it because maybe you didn't think about it in terms of optimization. And so we'll go through it briefly. Right? So basically it's function fitting. Right? Least squares typically is looking for linear functions, right? A linear function which maps a set of inputs to a set of outputs, right? So you've got basically you've got a bunch of data here. Maybe these are measurements, right? So measurement of, I don't know, I think the classic example in your high school class is a spring force, right? You have an extension of the spring, right? And then a resulting force. Right. And so you take some measurements, and maybe you're like pretty bad at measuring force, or you're pretty bad at measuring length, and so these measurements don't look perfectly linear. And so what we try and do is we fit a line to these measurements in order to determine the spring constant of the problem. Right? So the slope is the spring constant. Okay. So right, so we got data, above and below. So we have these data points, and we want to fit this line. And what's the optimization problem here? Obviously, we can't fit a line that precisely hits each of the data points. And so instead, we're going to find a line which minimizes the distances, the sum of these distances, or actually, in this case, the sum of the squares of the distances, delta x1 squared, delta x0 squared, delta x2 squared, and so on. And we want to minimize the sum of the delta x's, I squareds. Right. So that's sort of our prima facie problem. That's what we want to minimize. So how do we get those delta x's? Right. So first of all, we have to think about what our variables are. Right. Variables. So what are our variables? Well, we've said we want to fit a line. Right. So what are the parameters which define a line? Right. So if our input is multidimensional and our output is scalar, we can define a line as follows. Right. We can define a line as as a slope and plus a constant offset. So technically, this is not this is an affine function, not a line. But okay, we don't have any well, maybe we don't have many mathematicians in the room, so we'll just call it a line. Right? And so what then is our variables? What are we trying to choose? Well, our inputs, remember, so b equals, right? Our inputs to this line, right, this curve, are the x and x-axis. So the slope multiplies the x variable, the independent variable, right? And so what are we choosing? The slope is our first variable, and the second variable is our offset. So this parameterizes every possible line on the variables. The data is not a variable, right? The data is given. We can't choose the data that we have, right? Well, I guess we can leave out some data, but let's ignore that problem. Right? So the variables are the parameters of the line, the slope, and the offset. Okay. So that's the things we have to choose, right? So where do they lie? Well, the slope, if this is an Rn, so a vector, right? Then the slope is also a vector of length n, right? And the offset is just a scalar. Right? So, well, actually, if our output is an Rm, then our offset will actually be a scalar as well. But we're considering vectors and not matrices here. So we'll ignore that bit. Right. So those are our variables. And now, so we can add that bit to our optimization problem. We're minimizing, clearly. We said we're minimizing here. And so what are we minimizing? Well, we're minimizing these distances, right? So we're minimizing the distance from this data point, which is AI, to the value of the line, or sorry, that's BI, to the value of the line at AI, f of AI, right? So we're minimizing that distance, or the square of that distance. So we're minimizing the distance between f at AI and BI. Now f, of course, we've said it has this form, right? So we'll just go ahead and plug that into fi to get, right, this vector form. So now we've got the sum of the squares of the distances from f of AI to BI, represented using our variables here. So our variables are here and here. Those are our two variables. We have the field under which they're occupying. They're in Rn and scalar. And so we have a form of optimization. Now, do we have any constraints on our variables? No, I have not added any constraints on the variables, so we can assume that they're unconstrained at this point. We could add some if we wanted to, but it would be a different problem if we did. So we have a relatively straightforward optimization problem. We can make it look a little bit simpler, a little bit neater by putting all these things in a line, right? Because we're summing these squares. We can expand out this square, and we can just put it as in matrix form, right? The matrix whose rows are the slopes right here. Yeah. So not sure actually why I put the ones here in the end, but that's okay. We'll ignore that. So it's a matrix whose rows are the data points. So these are the data points. And so really the A is itself part of the data, and this vector B is also part of the data. So we've formulated our objective function in a very nice quadratic form, right? So it's a square, it's quadratic. Our variables are z, which lie on Rn, also b. I should mention them. I think the reason I put the 1 here is because I actually originally did n plus 1, so we'll actually get rid of those 1s and make our life consistent, and b and r. Right. Oh no, actually that doesn't work out. So z and Rn, and the last value of z is z naught, I guess. Right. So that's actually z and then z naught there at the end, and that's why we have the 1. Right. So it's a nice clean optimization problem, least squares, and of course we know that this is solvable, right? So you get a nice nice little story about how it was solved, which is, I think, illuminating in some ways. So depending on who you ask, the problem was solved by Gauss. And there's a nice little story about Gauss. So Gauss was a difficult mathematician to like, let's say. So he was around. This is about the time of the Enlightenment. So lots of things going on, including the French Revolution, which he was adamantly against. So he was a monarchist. Not very popular among pretty much anyone, but generally credited as perhaps the greatest mathematicians. Prince of mathematicians is what was called. Anyway, he's a professor of astronomy, actually, not mathematics, but his contributions are mostly to mathematics. And what's really interesting about Gauss is he had this lovely saying. There's also stories about Gauss, but he had a motto, right? Pauca sed motura, I think, which is in Latin. So which means few, but ripe. So his motto was "Don't publish a lot." Which is very much in contrast to the way people are today, which is obviously you're not a good researcher if you don't publish hundreds of papers, right? So Gauss actually published very few. He would take 30 years, in some cases, to publish his work. And quite often he would only publish the work when somebody else had already published and beat him to it. Right? So he was constantly getting was scooped on various mathematical results. At least that's what he said. Right? So anyway, that was his motto: is publish few, but when you do publish them, make them great, right? So make mathematics great again, if you want. So he's credited with lots of discoveries, right? And of course, particularly relevant to us is he's credited with, by some people, with least squares. I put maybes because he didn't actually publish them first, so he just claimed them after they were already published. But so Gaussian distributions, so in probability, right? The Gaussian, right, or normal distribution is named after Gauss. Gauss's law in electromagnetism, right? Named after Gauss in his collaboration with Weber. I don't know why Weber didn't get named, but Gauss came up with the formula or the model, which we still use today. Non-Euclidean geometry, parallel line theorem, right? And of course, least squares. So actually, before I do least squares, right, there's a very interesting story on the non-Euclidean line theorem. So this is like something that dates back to the Greeks. It says if you have two parallel lines, right, can you prove that they will never intersect, right? That's parallel line theorem. It was unproven until, not Gauss came up with a very nice proof that showed that in fact there's one more assumption you have to make, that the geometry has to be Euclidean, right? And then you can prove it, right? So Gauss heard about this lovely result, and he wrote a very nice letter. I forget who proved it actually, which goes to show like how Gauss trumps these things. He wrote a very nice letter to the author, where he said, "I would love to congratulate you on your contribution, but if I were to do so, I would only be praising myself, for I discovered this, in fact, many years ago, and therefore I don't want to be non-humble by praising your discovery, which is actually my discovery." Right. Which is like perhaps the most backhanded compliment I've seen, but otherwise it is a good insight into how Gauss operated. Right, he would come up with these things and then sort of meditate on them for 20 or 30 years before publishing them. Usually after someone had also already done so, but he would publish them better and then claim credit for them. And the least squares is another of those cases, right? So Legendre, a very famous mathematician, actually published the first solution to the least squares problem in 1805. And in typical Gauss fashion, right, he claimed himself to have solved the problem 10 years earlier in 1795. And in fact, he did publish a far more rigorous, mathematically rigorous solution to the problem in 4 years later in 1809, not to be rushed into such things, right, of course. But it was a much better solution, and in fact introduced another thing he's well known for, which is the normal probability distribution or Gaussian distribution. So I guess by waiting 14 years, right? He killed two birds with one stone, sort of unified these concepts. Which is better? I don't know. But it's hard to argue that Gauss is not a great mathematician. So, in any case, for applications, however, it's not just mathematics. You saw he was a professor of astronomy, right? This was actually motivated by the problem of Ceres, which is a mini planet floating around in the asteroid belt. Here it is. Right, there's Ceres right there, out beyond the orbit of Mars, and someone noticed it. Piazzi noticed it in 1801. Observed it 12 times, and then took a nap or something, and he lost it. Right, never saw it again. Right, so. Lost it after observing it 12 times, and no one could find it again. Right, no one knew where it was. It has a fairly elliptic orbit, right? So it's pretty hard to find. So you had the declination, right, ascension, And this is pretty problematic because the observations were only spread over 1% of the orbit, so a very short part of the orbit. Right, so very little data, right, to fit. Right, so the least squares problem is partly motivated by this problem of finding Ceres. Right, notice it's like it was lost in 1801 prior to Legendre finding the least squares solution. So actually, Legendre solved the problem, but Gauss actually, after resolving the problem, you applied the algorithm and then calculated the orbit of Ceres and predicted where it would be, and it was actually used it to discovered it sometime later in 1801 in the correct location. Right. So there's some evidence that he had actually solved the problem much earlier. So he predicted the location, it was refound, and problem solved. So these these optimization problems, of course, least squares was all well known, have very important applications. Least squares, however, is probably the easiest optimization problem you've ever encountered. It's unconstrained, it's quadratic, the variables are linear. It's all very, very, very straightforward. And in fact, it's even better because there's a closed form solution, right? Closed form solution. This is, of course, what people liked back in the day. They didn't have algorithms. Of course, Newton had his Newton's algorithm back in the time of Newton, but generally people preferred closed form solutions. And conveniently, the least squares problem has a closed form solution. So it's just a series of matrix multiplications times your data. Your data is in there, and so you can solve the problem. Here's your data, data, data. Right, and you may recognize the solution, right, as a generalization of the inverse. Right, you're inverting, more or less inverting the linear function. But this is, of course, the pseudo-inverse, right? Alternatively called the Moore-Penrose inverse. I forget who Moore and Penrose are. I'll have to look it up. In any case, it has a closed form solution. It's easy to calculate, so that's a solution to the problem. Very tractable, except, of course, nowadays we have really big data sets and with new data coming in all the time, and so there's a big interest in what's called recursive least squares, and that's still more or less an open problem, actually. Recursive. Like, how do you adjust your fit when you get new data, right? So without completely resolving the problem. So that's somewhat open. There are some good algorithms for it, but it's not completely solved. This assumes, of course, that you have more data points than you have actual variables, right? That makes sense, right? You're trying to identify a number of parameters, and you better have more data than you have parameters, right? If you only have the same number of data and parameters, you can still solve the problem, but it doesn't work very well. Right? So that's the least squares problem. Now we can get to something slightly more advanced. So least squares is fairly obvious, right? Now we can come to something a little bit more interesting, which introduces another class of optimization problems, mixed integer linear programs specifically. We'll talk about that later. MILPs. And it's called max cut. You may or may not have heard of it, so if not, I'll describe it, and it's not that hard to formulate. Basically, we've got a bunch of nodes, right? And you want to try and they have certain affinities for each other, right? So every node has a certain affinity. We can label them 1, 2, 3, 4, 5, right? And you want to find a way to partition the nodes into two groups. Partition the nodes into two groups so as to maximize the pain of separation, for example. So let's, if you think about it as, let's say, students, right? These are students in the class, 1 through 5, and they have certain affinities for each other. So, like, Dave likes Ken with a certain affinity. He likes, say, a value of 0.5. and Ken likes Carl with affinity 2, and Carl likes Emily with affinity 1, and you can even make these negative, right? So like Emily really doesn't like Ken, you can put a negative weight on there if you like, -5, something like that. So the max cut then is how to group these students into 2 groups such that they're all, so the total annoyance of all the students is maximized, right? So if I separate Dave and Ken, they're annoyed at value 0.5. If I separate Carl and Ken, we get 2 points. If I separate Emily and Ken, we get -5 points. So obviously that's not a good choice. But maybe Emily really likes Sue here, so there's like a 10 there, right? So that's a big cut, right? Anyway, so we want to partition the students so that they're most unhappy. I sometimes feel like we have this, we formulate this problem at ASU in terms of scheduling classes, but okay, let's leave that alone for the moment. So how are we going to formulate this problem? Right? So I know more or less what I want to maximize, unhappiness, right? How do I formulate it? What are my variables? Right? So now you're supposed to think and, well, give me certain suggestions. So we have to quantify these are numbers, right? So a typical trick is if we have like 2 options, right? Remember blue, red, right? To give a number to each option. So for each student, right? For each student we have a variable, which is the option, right? And so option 1, so group 1, right? If we assign student I to group 1, then we say xi is 1. And if we assign student I to group 2, then xi is 1. So -1 or 1. So it's sort of 2 choices. And we can make these any numbers, right? We can make them 0, 1. We can make them 0, 10. You know, it doesn't matter, right? But we have to give them a number, and so we assign the xi to a value if the student is assigned to group 1 and another value if it's assigned to group 2. Okay. So that's a way of dealing with our variable definitions, right? So now we've defined our variables, xi, which we constrain to be in, this is how we write that constraint, x in, and here this is how we write discrete sets, -1, 1, right? So we've defined our variables. There are n of them, and they have to be either 1 or -1, right? So we've defined our variables. So now how do we formulate the rest of the optimization problem, the objective and constraints? Okay. All right, so we've defined our variables, right? They're in x is in -1, 1 to the power n, indicating there are n of them for n students. Right? This type of constraint is generally referred to as an integer variable constraint or a binary variable constraint. So binary is typically, I don't say it's a binary because binary is typically 0, 1. Right? So we're calling it an integer constraint. Right? And we can, well actually I call it a binary constraint, but technically that's wrong. So these can be incorporated of 2 ways. We can say this directly, right? We can use this formulation. Or equivalently, we can add an equality constraint, which just says xi squared equals 1, which there are only 2 solutions to that. So that implies that xi is either -1 or 1. Right. So there's 2 ways we can incorporate it explicitly as a constraint and allow x to be a real number, or we can just put it right into the formulation of a binary or integer programming problem. Right. So that binary and integer variables in YAML can be declared directly, actually. Now we'll come back to and discuss why these are hard to solve, but you can declare them directly using these 2 commands. Right? So if you want x to be an integer variable of length n, right, just say x equals int var in YAML. Right? in YAML. X equals int var, where n is the length of the vector, right? So that constrains everything to be an integer. But that means it can be that 1, 2, 3, all the way there. So there's an infinite number of choices, right, to infinity. Conversely, if you say x is bin var, right, or y is bin var in this case, that makes all the elements of y binary variables. So that means 0, 1, I believe. I double checked the documentation on bin var for me. Say help bin var, but I'm pretty sure that it's 0, 1. Right. So again, YAML makes these types of variable constraints relatively easy to implement. You don't need to do this, right? You don't need to do both of this. Just do this, right? Don't do that. So this is right. It's right. This or this. Don't do both, right? Because that would be redundant. Although it wouldn't change the solution to the problem, but typically it's able to handle these type of constraints better. Okay. So that's the variables, right? Now what about the objective? Well, here, remember, we want our objective to have the sum of the costs of separating the variables. And here you have to be a little bit clever, right? So basically we want to say we want to add wij to the objective if, right, xi does not equal xj, right? So we want to add wij to the objective if xi does not equal fj. But this is like an if logic. How are we going to incorporate this if logic? No easy way to do that, right? You have to be clever, right? So there's there's a couple ways of doing it, right? You can incorporate the if logic into the constraint. You could have a third variable or something like that. But the way we do it is really rather clever. I mean, I didn't come up with it, so I'm not praising myself. I don't want to be like Gauss, but it's rather clever. It's just not mine, right? And we notice that, right, because we've defined these xi as 1 and -1, right? So 1 or -1, right? So if they're both the same, that means they're in the same group, right? So if they're both the same, then this product here, no matter if the group is 1 or -1, that product is still 1, right? So if they're in the same group, this is 1, and 1 minus 1 is 0, right? So if they're the same group, this term right here is 0. And if they're in opposite groups, right, 1, -1, for example, or -1, 1, no matter, right, which group, which one student is assigned to which, the product of this is -1. And so 1 minus -1 is 1 plus 1, which is 2, right? So this product is 2 if they're in different groups. Right, and so we can we use these numbers to like find little tricks for simplifying the optimization problem. And so what we can do, right, then is we can add that to the objective. So we want to add wij if xi does not equal xj, right? So if xi does not equal xj, right, then this is 2. And so we have to add the 1/2 here, right? So we add it in, right? So if multiply those two together, and right, it's just 1. And then if xi equals xj, this term is 0. So we have some other things which are 0, but of course they don't get added in if you multiply by 0, right? And so this is a clever way of formulating the objective function to take account for this sort of logical type construct. Right? And so as a result, we get this which is technically an integer program, although it's really a binary program, where we've added the constraint xi squared equals 1. So it's there's no other constraints, right? We don't have any other constraints. So this is actually still an unconstrained optimization problem, right? Except for the fact that our variables are bin vars or int vars, depending on how you think about it. Right? So, right, a clever way of introducing the max cut problem. Now, just because it has a very simple formulation doesn't mean it's an easy problem. In fact, max cut is NP hard, which we'll talk about later, which means it's very hard to solve, right, for large scale problems. Right? And so it's actually, despite the fact that we can formulate the problem, doesn't necessarily mean we can solve it. So just an illustration, right, of the problem, right? So if we assign the solution, right, is if we assign students 1, 2, and 3 to group 1, and we assign students 2 and 5 to group 2, right? Then the objective, we plug these values into the objective function, we get a cut with value 4. And that's where 1 and 4 don't care about each other, 2 and 4 don't care about each other, 2 and 5 don't care about each other, but these guys all want to be together. Right? So we can accommodate, we can make these guys suffer to a degree 4, right? So that's quite a lot of suffering. These guys are, not everyone is unhappy, right? 3 and 4 still get to play together, but 2 and 3 and 5 and 4 still get cut. Okay, so let's move on now to something that looks a little bit more like a controls problem. Right? This is controls, and we want to say that, right, controls problem can be formulated as optimization problems. So, okay, well, prove it. Right. So this is an optimization problem which goes by many names. Right? So one name is LQR. One name is dynamic programming, but it's equivalent. So let's think about this problem. So basically, we have a set of dynamics, discrete time dynamics in this case, although it can be continuous time, which govern the effect of how our input affects the state. Right. So this is an evolution equation, right? But it's an equation. Right? We have an initial condition as well. Right? So there's our initial condition. And we want to choose our input. Right? So that's obviously a variable. We want to choose our input such that the solution to this equation, minimizes a cost function, right? And this is a standard controls related cost function. You have a weight on the terminal value, the end point, the last time step, terminal cost, and you have a running cost, right? Which is the sum of some quadratic form in our states and some weight on our inputs, right? We always put weights in our inputs into the objective function because otherwise optimization problems get very aggressive and give us infinite inputs, right? Extremely large inputs, which isn't practical, right? So we always have to put some kind of regularization term in here. And that we'll have to do that throughout the course. Right? So this is regularization. It weights our inputs so that we don't go crazy with our inputs, make them infinite or something. Right. So this is a sort of standard LQR problem, which we see all the time. Right. So what are our variables now? Well, clearly our variables are our inputs, right? But there's something else which appears. How do we map this relationship between our inputs and our states? Right? Well, the only obvious way to do that is to make our states themselves variables, right? So one way of thinking about it is to make the states variables. Right, so make the states variables. And notice here I put x and u, right? And that's to indicate, right, without the k, to indicate that this is over the entire time span, right? So u of k for k equals 1, right, all the way to n. So all of those are variables, and all of the states are variables. Right, so that's fairly straightforward. We can do that, and then we have our objective function, which now is a function of the variables. Right? Variable, 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 variable. Right? It's a sum of the variables at individual points in time, so it's just like a sum of all of those together, and then the final value. Right? Now, however, right, how do we represent the relationship between the inputs and the state, right? The trajectory, right, that is produced by an input, right? Well, that's where we add in the dynamics, right? So we can think of the dynamics actually as a constraint which couples the inputs to the states and couples them in time, right? So the next, so it's causal. So the next time step is a function of the previous time step state and the input at that time, right? And then we have a final coupling here at the initial time, which gives us our initial condition, right? So we can formulate this optimal control problem, right? We're trying to find an input which minimizes the cost of the state as an optimization problem, right? But one with lots of variables, right? If n is the number of time steps, then it's the dimension of x plus the dimension of u times n. So lots of variables are here. Right? So this is a really big optimization problem. Big. And by big, we mean lots of variables. And lots of constraints, because we have n of them. Right? So really big. Lots of variables, lots of constraints. Right? So this would seem like, you may not know anything about optimization, but you say, well, this is like a lot of variables and a lot of constraints. It seems kind of intractable. Right? Okay, so it sort of is. Except for the fact that we have this nice result, which dates back to the 50s, which says that this form of optimization allows us, can be reduced to a set of smaller optimization problems, one for each time step, so n time steps. So this is actually a nested sequence of optimization problems. So starting at the final time and going back, right? So it's indexed by our start time, which is 0 in this case. And then for each subsequent time period, we have a separate optimization problem, right, which doesn't depend on our previous states. Right? And what Bellman's equation, or the principle of optimality, says is that this very complex and large optimization can actually be broken down into a sequence of smaller optimization problems, which we can then solve one at a time. So we don't have a really big optimization problem to solve. So basically it says if we start anywhere along the optimal trajectory, this is the principle of optimality, that solution, right, will be optimal, right, just truncating the series, if we restart the optimization problem at any point along that trajectory. So if we restarted with that initial condition and just on that shorter time horizon, the solution we got for the big problem is still optimal for the small problem. We could take it all the way down to the last time step and just solve that last optimization problem and then go backwards in time. And that's what Bellman's equation does. Right? It tells us more things, actually. It tells us actually that the optimal solution, right, the optimal input is a function of the current state and not the history of where you were, right, or where you're going, right? So you can reduce the optimization problem to a set of n optimization problems only involving a single variable. Right? And this is a very important result. It also goes by the name of Dijkstra's algorithm. You may have heard of that. Which, in Dijkstra's algorithm, is what allows us to have the internet. Right? That's what enables packet routing. And it also, if you think about it, is what allows you to find the shortest path between your home and class, although very few of you are coming to class, and say none of you, using your iPhone or your Google Pixel or whatever it is, right? So if we think about that optimization problem, here's your house, here's class, here's all the roads, right? It's a grid, right? And the grid, right, has each of these segments has a weight, which is congestion, so time it takes. So each segment of road has a weight, right, which is the time it takes. And so what this says is that if you start at the endpoint and then work backwards, right, in various directions and truncate the paths which are too costly, and you can eventually get back to where you started, and that's how that's how path planning on the using Google Maps works, right? So it's the same algorithm that actually works for packet routing as well. It's how your packet knows how to get from right here, where I'm teaching this lecture, to you, wherever you happen to be. Right, it has to go through a series of routers, and the optimal route is determined using Dijkstra's algorithm. And of course, it allows us to solve LQR as well, right? The LQR regulator problem in discrete time, right? So there's this is a standard trick, right? Very powerful trick that people use. And it also allows us to solve the LQR problem. So the previous problem was open loop, right? So we're choosing our sequence of inputs, right? That gets us from point that optimizes that trajectory, right? We have this map from our sequence of inputs to our x. However, what the principle of optimality says is that actually our optimal input is actually only a function of the current state, and furthermore, right, because the optimization problem in all of these iterations doesn't change, right, that function of the current state is linear and doesn't change, right? So you can find a single policy, a fixed policy, that's the word they use, right, which relates our current state to our optimal input, right? So what this says is that we can eliminate, essentially, all of the variables x by just by using this relationship here, u equals kx. So this dramatically reduces the size of the optimization problem. So we don't need to optimize over u. We don't need to optimize over k. We're just solving over x. We're only solving over k. Right. So in a way, it's actually a slightly harder problem because we're actually adding this relationship, another constraint to each of these time steps, right? But, right, the nice thing is that when we do that, of course, we can actually solve for the trajectory explicitly, right? We can say x of k, or x, I guess, small k, right? We can solve for the solution is this sum of these. There's an explicit solution here, which I'm not going to write down, which is an explicit function of k, which depends on k. Right? So it's a sum of a plus bk x, right, to the k equals 1 to... this is the wrong formula. We'll cover the right formula later on in a subsequent lecture. But it allows us actually to eliminate the variables u and x from the problem. Right. So actually, in this case, we've added an additional constraint, right? That the u is a static function of x, parameterized by the variable k. Right. So actually, we should add the k variable in here. And what the principle of optimality says is this is actually equivalent to the open loop problem. Right? Closed loop and open loop problems are equivalent. Right? So they have the same objective, and a solution to one can give you a solution to the other. Right? So this is, we often cover this as the LQR problem in discrete time, but we're not going to get to that until a later lecture, so I'll sort of skim over that for now. Right. So how do we know if two problems are equivalent? So that sort of motivates the question of equivalence, because some formulations are considerably simpler than others. Right? So how do we know if two optimization problems are equivalent? So basically, our definition of equivalence, right? So what do we mean by equivalent, right? So two problems are considered to be equivalent if a solution to one, any kind of algorithm which can be used to solve one, can be used to solve the other, and vice versa, where the conversion is not too onerous, basically polynomial time. The conversion from solution to one to solution two is not particularly complicated. So here's just some examples, right? So 3 optimization problems, which are all equivalent. And they're relatively straightforward. They all have the same constraints, right? So the set of feasible set is the same. Right? But the objectives are all different. So now what do we mean by equivalent, right? Because obviously, right, if the feasible sets are the same and the objectives are different, right, they'll give you different objective values, right? In this case, what we mean is that the choice of variables will be the same, right? So in this case, we have that the optimizing value of x right is the same in each problem, right? And we have this is not a very good proof, right? I mean, it's very short, and so it can fit on one line. But just to give you a flavor of how these things are chosen, right? So basically, we can start by saying if x is feasible for any one, it's feasible for all of them, right? Because they all have the same feasible sets, right? So now let's assume that x1, we have some other solution x, which is not equal to x1 star. To say problem 3, I guess we got here. Problem 3. Since x1 is optimal for problem 1, we have that other value of x, also feasible, has to be greater than the value assigned to our optimizer, right? So their f of x is greater than f of x star. So therefore, right, if we look at the objective to the second problem, right, we just look at the objective, right? We have 10 of f of x, right, obviously has to be greater than 10 of x star, right? We just multiply 10 times both of those, right? And the 12 doesn't change that, right? In fact, actually, we could just strike 12 from the problem because we can't change it, right? It's one of those parts of the objective which isn't influenced by our objective, so we can always cut those off, right? And so 10 of x is greater than 10 of x star, so therefore x, that choice, is suboptimal for problem 2 as well, any other x. Now if we look at problem 3, we can also show it's suboptimal. Here we're trying to maximize, notice, right? Not min, maximize. But we notice that, right, that 1 over f of x at that other proposed point, because f of x is greater than f of x star, 1 over f of x is less than 1 over f of x star. And so 1 over f of x is less than 1 over f of x star, and since x1 star is feasible for all 3 problems, this, right, x is also suboptimal for problem 3. And so, therefore, any other point in the feasible set is going to be suboptimal for the other points as well. And so, the solution to 1 is a solution to 2 is a solution to 3. And so, all 3 problems are equivalent. Okay. So, this illustrates a few things, right, so it says a few standard tricks in optimization. First of all, of course, you can multiply it by a constant, and it doesn't change the solution to the problem. Another point is that max of 1 over the objective is equivalent to minimization of the objective itself. Right. So the couple quick tricks we can learn there. So that was in the objective, right? So there's a couple tricks for changing the feasible set, or at least the representation of the feasible set. So basically, any set of constraints are equivalent if they result in the same feasible set, right? Or don't change the problem, right? Here, for example, we've introduced an invertible change in the variables, right? So we have an objective function with a constraint, and here we've changed our variables slightly, right? We've said that our new set of variables is an invertible matrix times our old set of variables plus a constant. And what this allows us to do, right, is we can convert back and forth between variables for one set of one optimization to the other, right? Because, right, if x1 equals is this, well then x2, we just invert the matrix and maybe we can recover x1, right? So, right, if we just plug in, right, into this variable here, well, x1, x2 star, right? That's that's the optimization for the solution to problem 1. Well, that's just x, right? x1 star. And right, if x2 star is feasible here, right, then x1 star is feasible here if x1 and x2 are defined in this way. So the solution x1 gives us a solution to x2, right, given here. So if x1 is optimal, then x1 star is optimal, then x2 star defined here is optimal for problem 2 and feasible. Obviously, you can just plug it in and see that. And if x2 star is feasible for problem 2, then x1 star defined here is feasible and optimal for problem 2. Right? So invertible changes of variables result in equivalent optimization problems. So you can always change your variables if the change of variables is invertible. Right? So invertible changes of variables are result in equivalent optimization problems. So there's another trick, right, which is separation of variables, right? So variable separability, right? So for example, right, in here we have two variables, x and y, and the objective function, right, is a combination of a function of variable 1 and variable 2, right? But they're not coupled together in any way, right? So if that's true, then we can separate the variables if the constraints are also not coupled. And here we've decoupled the constraints as well, so that the feasible, we can represent this as x is in S1 and y is in S2, right? And if that's true, right, then this problem here is equivalent to min over x of f of x, subject to x is in S1, plus min over y in S2 of g of y. Right. And so we can decouple this optimization problem into two sub-optimization problems, each in a smaller number of variables, and then add the solutions together to get the solution to the other one. So if we solve optimization 3 and we solve optimization 2, then we can construct a solution to optimization problem 1, right, in this way. Right. This works only, of course, if the objective function is separable and the constraints are also separable. Right. Right. So if neither feasibility nor optimality are coupled in any way. So this only works if these are not coupled. So two real tricks: changes of variables and separability. Okay. Right. So we can also add redundant constraints to not solve the problem, and of course variable separability is what allows us to solve dynamic programming. We solve this nested sequence of optimization by solving the last variable first and then moving backwards in time. So those are a couple tricks. Now we'll talk a little bit about constraints. Right. All right. What is the difference between the constraint and the objective function? Well, it may seem obvious, right? I mean, an objective tells you what terms are optimal, and a constraint tells you which are feasible, but anything that's just feasible, right, we have no other preference for. Well, that difference is a little bit fuzzy, right? And so we can see that by looking at these two optimization problems here, which are also equivalent. So here we're trying to minimize f, subject to a constraint on g on x, right? But this would be equivalent to minimizing just a new variable t, right? So if we look at this function, right? So here's our function f, right? And say this is our feasible set, right? So we're trying to find this point here, right? Because that's actually we're trying to find this point here because we're minimizing. Right? So we're trying to find this point here. Okay. So we got a function, and we're looking at the minimum value of the function over the feasible set. Right. So what we can do, a trick we can do, is we can look for a new variable t. Right? T. And we can find, actually we should make t a little bit higher. Right, t. So we can look for the minimum value of t, right? The smallest, try and minimize t, subject to the constraint, right, that t is greater than f of x for at least one point in g. Right? So t is greater than x, right, at one point such that g of x is less than 0 in the feasible set. Okay. So there exists an x such that t is greater than f of x where g of x is less than or equal to 0, where g is the feasible set. Okay. So we can find the least upper bound on f, right, which is feasible. Right? So this allows us to transform our objective function to something which is maybe linear, whereas the original objective was nonlinear. Right? This is not a linear function. And this is linear. Right? So by introducing a single other decision variable and then adding additional constraint. Right? So this illustrates some ambiguity in the differences between objective function and constraint. And this is a standard trick, by the way. to move your objective function to the constraints. And it's useful because often like these are easier to deal with, sometimes easier. Right. So another example of a trick for manipulating your optimization problem. Some other equivalences briefly mention, right? Redundant constraints, right? You can always add an additional constraint which is satisfied on the feasible set, right? And then it doesn't change the feasible set, right? So for example, if your feasible set is x greater than 1, right? The set of x such that x is greater than 1 is not changed if you add an additional constraint x greater than 0. Right. So redundant constraints don't change the problem. Right. Easy to show. A little bit more subtle is the representation of the set itself. Right? So, for example, there's this classic representation of polytope. So a polytope looks like this, right? Actually, it's not a convex. We typically have convex polytopes. Something like that. Right? So there's two ways of representing a polytope. One is you take the vertices, alpha I, alpha 1, alpha 2, alpha 3, alpha 4, and so on. And you force, just add alpha 5 since we're there, we force x to be a weighted sum of those vertices. Right, less than or equal to 1. Right. So that's one way of representing a polytope. So that's the vertex representation. An alternative representation of the polytope, however, right, is to take these hyperplanes or lines, right, and we look at the intersection of a bunch of lines, right, half planes. So this half plane, right, would be, for example, x such that A1 transpose x less than or equal to b, right? And then we have another constraint imposed by this vertex, alpha A2, or A2 transpose x less than or equal to b2, and so on. For each hyperplane, we add a constraint, and then it's the same set, right? But our parameterization or representation of the set is very different. So, for example, in this case, it's represented like this, as C transpose X greater than or equal to B, where this is the, like in the least squares, right? That's where our rows are the slopes. And here, where we have some well, actually, this is an inequality constraint. We have an inequality constraint coupled with an equality constraint. Right? So two alternative representations of the same thing. The same set. Right. Oh, so sorry. I keep like going outside my box. Yeah. Well, how far down does my box go? Goes to there. Should keep that in mind. Okay. So new forms of equivalences. Lots of forms of equivalences. So let's now apply this to a fairly well-known optimization problem, although perhaps you don't think of it much if you don't actually know what machine learning is, as an optimization problem, which is machine learning. So specifically, we're going to look at the classification and support vector machine problems. And so what is this optimization problem? Let's take a look at that problem. So what we've got here are basically a set of labels, right? So the best instance of this problem is the Netflix problem, right? So the Netflix challenge, right? So the Netflix challenge is, so Netflix has like your movie preference data, right? So it used to be, right, when you watched Netflix, you would give it a number of stars, 1 to 10, 1 to 5. Now it's just thumbs up or thumbs down, right? Okay, so we'll do the thumbs up, thumbs down thing, right? So in particular, right, they have all these movies that you've watched, and whether you like them or not. So disliked or liked. And so it has labels. These are called labels, right? You've labeled a bunch of data. Or what is the data that you've labeled? Well, you've labeled the movie, right, you've watched. Well, okay. Movies are very complex data points, right? So it's not going to do data analysis on the whole, like, whatever movie you watched, right? So it actually breaks the movie down into pieces, right? Based on, like, is it an action flick? Does it have Demi Moore in it? No. Well, I guess I'm dating myself. Does it have Billy Crystal in it? Okay, I'm dating myself again. Does it have, Ashton Kutcher in it or whatever, right? So data on the movie, right? Parameters of the movie, right? How long is it? What's the budget? I don't know. There's lots of data for each movie, right? So metadata, if you want, budget, length, etc. All right, so I have inputs and labels, right? The labels are whether you liked it or disliked it. So they're binary labels, yes or no. And so this is similar to the what was it called? The max cut problem, right? We want to assign movies to labels, right? But that's of course where the similarities end. So basically, we have a sort of continuum of data, right? With these XIs, right? We have input learned data to learn from, and then we have future projections. Right? So basically, here's our this is say x, and so if xi equals x. yi, so there's two pieces of data there, right? These are the two pieces of data on the x and y axis here. Right. So we have a bunch of data which says that, okay, so for points in this area, right? So they have negative labels, and these points over here have positive labels. Right. And the support vector machine problem is to find a rule which separates these data into intelligible, that separates the data, basically. We want to find specifically a line, right? Right? Parameterized by the variables w and b, such that if the data has the label -1, it's above that line, and if it has the label +1, it's below that line. Right? So we want to find a separator. Right? So this allows us to classify data as 1 or -1, depending on if it lies above. This is -1 region, or below that line. Right. So it's a classifier. This function is what's called the classifier. Right. I won't get into what support vector machines are, what the support vector is right now, but I think we'll maybe discuss it later. But anyway, we want to find a classifier which takes our data, right, the data we want to learn from, and then such that W transpose X minus B is greater than 0 for all the data points Xi in group 1, and the opposite if Xi is in group 2. Okay. So it's less than 0 if it's group 2. And also we want to maximize the distance between those two groups, basically. So find a classifier which takes data and predicts which group it is in based on whether it's above or below this hyperplane. Right. So just a brief word on hyperplanes, right? It's a word for line in n dimensions, right? Because we have lots of data, right? There's lots of length, Ashton-Kutcher, budget, so forth, lots of variables, right? So this is a line in that very high dimensional data space, right? So hyperplane, right, is the equality constraint version, and then a half space is the space above or below that line, right? So above or below a line, hyperplane. Right, so here's the hyperplane, then in this two-dimensional data set, which looks suspiciously like a line. And then that's one half space. And then above it is the other half space. Right. So basically we want to assign we want to make sure that the negatively labeled data is all below in one half space, and the positively labeled data is above. And here actually we've got misclassified points. It's not always possible. This is not always feasible. We'll talk about that in a second. Right. So that's the optimization problem, and we'd also like to, of course, have an objective. And the objective is to maximize the distance between the data above and below. Right. So what's our constraints? Let's look at the constraints. We'll talk about the objective in a second. So if you remember our constraints, well, they're sort of if logic, right? Logical. Xi is in group 1 if this is true. Xi is group 2 if this is true. Right? We had a similar problem in the max cut example. Right? And so actually we have a similar solution, but not exactly the same. Right? So basically we're going to get rid of the if logic, right, by using the sort of binary nature of the labels. So plus 1 and minus 1. So basically, right, we want this to be greater than 0, well, or 1 in this case, when yi is plus 1, and we want it to be less than 0, or less than negative 1, when yi is negative 1. So this is obviously, it's somewhat obvious what we're going to do here, right? So if, when we add our constraint, we take this term here and we just multiply it by the label, right? So for each label we have a constraint, right? So this makes makes greater than or equal to 1 if y is greater than 1, and then it flips the sign if yi is negative 1, right? So So if yi is negative 1, right, we can multiply or divide through by negative 1, and then this becomes, right, so that allows us this trick, right, of multiplying by the sort of binary choice, allows us to formulate these as equivalent optimization. It allows us to formulate the constraints in a way which doesn't involve logic, right? These logical variables, right? These binary classifiers take the place of logic. Right? Okay, so that's the constraints, right? Now we would also like to maximize the separation between the data sets, right? So basically, we've got here, this is a classifier, right? And what we want to maximize is this is actually, ignore these misclassified points. They don't exist. What we want to maximize is the distance, right? The parallel distance until the hyperplane intersects these points versus these points. So we want to maximize this distance, b. Okay. So how do we do that, right? So how do we translate that into our variables? Well, that's actually why we chose that we had made the constraint stricter, right? So obviously, if it's feasible for some W and B, it's with greater than 0, it's satisfiable for 1 because we could just scale up the W and B. The variables W and B. Reminder, those are the variables. Until the constraint becomes greater than 1 or less than -1. Right. So again, that's also equivalent optimization problem. But the key is, right, now we can say that, right, what these hyperplanes are, right? So these hyperplanes are these two hyperplanes. W transpose x minus b equals 1 and W transpose x minus b equals -1. So that's hyperplane 1 and that's hyperplane 2. And now we want to maximize the distance of them, right? So because we scaled up our variables a little bit and or normalized really the scale of the variables, we can find an expression for the distance between these two hyperplanes, which is 2 over the norm of W, right? So that allows us to find that distance, right? So, right, this is these are our variables. Notice that B doesn't appear in the objective, but it does appear in the constraints. And so we formulated an optimization problem, which we can now state relatively simply. A final step, however, right, is we want to, remember we want to maximize this distance. So we want to maximize this distance. And so we're going to do that standard trick that we talked about earlier, where maximization of 1 over a function, 1 over the norm of W, is equal to minimization of W itself. That's a trick we already covered. Right. So we've done several tricks in order to formulate our classification problem as something which is relatively easy to understand. Right? So it's got a quadratic objective, which is convex, and it's got a bunch of linear constraints. And remember, W and B are the variables here. Yi and Xi are the data. There's lots of them, one constraint for each data point, but still relatively scalable. Right. So this in several of these pictures, of course, we've shown misclassified points. And this is a standard problem because if you don't, there's lots of data sets which are noisy. Like you may be crazy and really like movies with Tom Hanks in them, I'm sorry, no classifier could ever predict that, right? I mean, it just makes no sense. So there's just there's no accounting. There's just sometimes you just can't account for data with at least with the variables you're given. So in that case, we usually relax the constraints on machine learning problems because there's no way to separate these two data points here, right? I mean, there's no separating hyperplane for these two data sets. So we allow for that, but we penalize it, right? We penalize misclassified data points. Remember, objective functions, right, can have multiple parts, right? We may be interested in the distance, but we can also allow for other terms in the objective if we include the weighting on that objective. Right. So this is a penalty for misclassified data point. So, well, now it's a sort of an unconstrained optimization, right? Because we've moved this constraint. It's no longer a hard constraint, right? We've moved it into the objective, right? Right? Which means we can violate the constraints, but we have a penalty for doing so. Right? So in a way, right, when we add these penalties, that's a lot like least squares, right? And in fact, actually, these machine learning problems are very similar to the least squares problem, where the least squares problem is only, right, a function of these errors, right, in classification. Right, how far off your classifier was. We don't have any objective where we're trying to separate the data points, maximize the separation. So least squares is similar, but we don't try and separate. But there's no separation. So, all of these problems are trying to do similar things, right? The advantage of the machine learning problem, or one of them, is that it can be used to solve very large data sets. So it's just a form. In this case, this is a very simple linear set of linear constraints, right? Can be represented as A transpose X less than or equal to B, right? Well, not, I should say A transpose W. Right, and right, and then we have just a quadratic objective, which is relatively easy to solve, and they're very efficient algorithms for solving machine learning problems. There's one on your homework, right, where you just take this classification problem and you formulate it and you solve it using LMIP. Right? If you go here to the link, there's you can go to the UC Irvine set of very large data sets. For example, the IRIS data set has, actually, and that's not the number of data points, but there's lots of data sets, and they have, you can see the number of data points in them. That one has 150 data points. We can see whether you're going to like a wine or how good the wine is. That has 5,000 wines in it, so if you want to predict if a wine, go to the grocery store, you want to see if the wine is going to be good, you can use your classifier. This has n variables in it, so n, features, right, is what they're called in the data. So that's the dimension of x, right? So lots of data for very interesting problems, allows you to solve all sorts of things, including whether you're going to like a Netflix show. Right. All right. So finally, before I take a brief break. Right here, I'm going to take a brief break. I would sort of summarize some of these equivalences in sort of a more basic set of equivalences. So we introduced the optimization problem as having this form, right? Where you're minimizing a function or maximizing a function of a variable x subject to a constraint parameterized by the functions g on the variable x, right? So that's what we saw. Also, you also had the hi of x equals 0, but we're ignoring that for now. Okay. So we talked a little bit about one part, which is that there can be equivalent representations of the constraints. So an alternative representation of the constraints. So any alternative representation of the constraints is an equivalent optimization problem. And so we can take that to our logical conclusion where we just think about the set or the optimization problem not in terms of the G, but in terms of the set itself. And that gets around, right, the issue of representation of the set. Avoids the question of representation. So in this case, right, this is how you represent the set, so you can obviously create the set. But geometrically, we think of these as a set of points, right? It looks like this in that n-dimensional space. And the question of how we represent that point is really immaterial to the set itself, right? So any representation of that set is valid. In fact, we can, like, say, over-represent the set, or we can under-represent the set. So it's a very useful conceptual framework for thinking about optimization problems. It's thinking about them in terms of optimization over a set, right? That's a geometric representation. So this sort of encapsulates those equivalences that we talked about between representations of the set. Any two optimization problems are equivalent if the set is the same, right? Good. Likewise, right, the objective as well. We talked a little bit about the objective function being their equivalent objective functions, right? We can again parameterize those equivalences by moving the objective function to the constraint set, right? So we sort of parameterize that set of transformations, right? Before this was t, now it's gamma. By instead just minimizing this gamma, subject to the constraint that gamma is greater than or equal to f of x for some point in the set, right? There exists an x such that gamma is greater than f of x, and the set is, and x is an s. Right? There exists, so we want to find the smallest gamma such that there exists an x in the set such that gamma is greater than f of x. Right? And this allows us to formulate the optimization problem, right, with a linear objective by moving the objective to the constraint set, and then we can think about this constraint set geometrically. So we can sort of have a pure geometric representation where we have a linear objective, which is the simplest possible, subject to that gamma being in the set, right? And so then the set, of course, becomes very complicated, but again, it's a pure set, right, representation. Right. So as we move through these equivalences, right, pure functional representation, functions, to a geometric representation of the set, to an entirely geometric representation of the problem, right? This allows us to do two things, right? First of all, we can conclude that really optimization doesn't actually need an objective function, right? It's the constraint set that matters, right, in a way, right? So, for example, if you have an algorithm for determining feasibility of a set, right? If you can determine whether this set is feasible, right, you can solve the optimization problem, right? If you have an oracle, it's a little bit more complicated than that. It assumes that some convexity properties on the set. But, right, it's that's what it is, right? Feasibility, solving the optimization problem and determining feasibility of the set are intricately related, right? And we can see that when we go to what's called the bisection algorithm, right, which just takes feasibility. If you can determine feasibility of the set, it shows how to solve the optimization problem, right? So suppose, so the bisection algorithm is something we use quite often, actually. It solves the problem under certain conditions, mostly converges to the optimal, right? It can be a problem if, like, your feasible set, there's another part of the feasible set down here, right? So it'll find this, or maybe there's another part of the feasible set over here, right? So there are limits to the bisection problem. But anyway, we'll talk about the bisection problem anyway. So basically, if your feasible set is convex. So suppose you can determine, so for a given set of values, a given variable, you can determine whether it's feasible, right? So let's just, if we move to the pure geometric problem, our variable is just gamma, right? So basically, here we've got gamma, and we want to determine the largest gamma such that this is feasible. Right? So how do we do this? Well, basically bisect. Right? So we basically say, well, okay, this is our entire parameter space, right? Gamma. So we have a gamma min and a gamma max. Right? We start with that region. How do we choose our gamma max and gamma min? No good guidance for that, right? We just want gamma min to be like negative 10 to the 6 maybe, and gamma max 10 to the 6, right? Or something like that, right? So we got upper and lower bounds. We need those. So what we do basically then, right, is we bisect our feasible space, right? So that we find the average, gamma min plus gamma max, divided by 2. And we test whether it's feasible, right? So basically we're trying to find actually it looks like in this place, this type we're finding the minimum, right, gamma. So we should actually make this min. And we test whether that's feasible, right? Okay, well, it is feasible. So it's not so feasible. So the feasible set is not empty, so feasible. Check. So that's feasible. Well, then that puts we can adjust our lower bound to gamma min there. And we can bisect again, right? So now we bisect, let's see, where did I put it here? Gamma 1 here. Here's our next bisection. Right? And so we say, well, that's also feasible. So then our actually, no, we are doing maximization, right? So we want to find max such that we're in the feasible set. Right? So we know that our gamma max must be above that, right? So we set this as our new gamma min. Bisect again. Now this is infeasible, right? So I can do x. Oh, that's x is too small. Okay, go by x. So let's do. All right. Well, so not feasible. So we know that our max is below there, or our min. Yeah. So that's our new gamma max. We do a bisection there. Check. X. Check. And so at each bisection, the upper and lower bounds on our maximal gamma get smaller and smaller. This box gets smaller and smaller. And in fact, it decreases by a factor of 2 at each time step, right? And so after k time steps, right, we can know that our optimal gamma is within the original distance, right? That's the original. This is A and this is B, right? The original distance divided by 2 to the k, right? So this is exponential convergence. So this is very quick, relatively quick convergence. It's not great, but it's relatively quick. Right. So this mostly works if your feasible set is convex. Of course, right, what would have happened if, right, there was another feasible set over here, right? Well, then I would have wrongly concluded, I would have wrongly assigned my gamma max here, right? So this would have been incorrect. Because, in fact, the gamma max is up here. Right, so it does assume that our set is convex, right? So, but in general, right, if you have a convex optimization problem, and we'll talk about convexity in a bit, you can solve the problem in the purely geometric form if you can determine feasibility. So bisection, 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 and then we get to the minimum, max in this case. Right. So I'm going to actually take a break now and come back to the question of what problems we can solve after the break. So stop now and leave you to it and come back shortly.